because Vincenzo had his son Galileo Galilei study music, and maybe that's what got him inspired.
Always important to recognize and to promote the connections between science, the arts, and the humanities, and to do what I'm about to do safely without tripping here. So thank you very much. And now I call your attention to what I'm holding in my hand here. What does it look like?
A ball and a string.
How big is it?
Not that big.
Do I have to ask all the questions myself? You're telling somebody listening to you on the radio, on the cell phone. What does it look like? A ball, you said, okay. Is it a big ball or a small ball?
Baseball size.
What am I doing with it? Suppose I do this with it. Is that interesting?
Yeah.
Kind of interesting. Suppose I stop it, and there's a little switch here. Suppose I turn the switch on. Now what do you see?
Rolling ball.
And what should I do next?
Spin it again.
Do it like this?
Oh my god.
How about turning the lights down? Let's see if we can see it better. Is that cool?
It's like a game.
Wow. What colors do you see?
Blue, red, green. Blue, red, and green. Red, green, green.
Okay, let's slow it down, slow it down, slow it down, slow it down. Stopped. You don't see all the colors anymore. Well, you kind of see them, right? Right? All right. So now, when I was rotating this, am I spinning? Am I rotating? Is it moving in a clockwise direction or counterclockwise direction? For you, it's what? For me, it is clockwise. Let me show you. See, if I turn it around like this, I haven't changed yet. I don't want to get hit by it. I got hit by it. Just doing it like this. See? Okay. Let's do this slowly. You see that? It's still now. Whoops. All right. So with the lights up, please. The eyes receive a lot of information, colorful information. And then the mind tries to make sense out of this information. So what we see and what we perceive may not always be the same thing. So I want you all to think about, why is it when I rotate this, you see the colors that you see, compared to when I don't rotate, right? So, and you know, you'd like me to give you the answers to all these questions, but I'm not going to. Because I want you to think about them, and I want you to engage in satisfying your own curiosity. I turned the switch off. I put the ball back in here. I walk through carefully. And I'm going to do an experiment here without tripping on the cords. I'm going to light a candle. Can you see the candle lit? I'm going to take a balloon, inflate the balloon. Let some air out. I'm going to set the balloon on the table. I'm going to pick up the balloon. What do you think is going to happen when I put the balloon on top of the flame?
Pop.
You sure? Okay,
Unless
let's try.
there's water in it.
You're right. All right, I have another balloon, same size. The flame went out too. All right. What do you think is going to happen when I put this balloon on top of the candle?
Not pop.
You think it's going to pop? We saw the other one pop.
Not
Let's
pop.
see.
No pop.
Is it popping?
No.
How come it's not popping?
Water in it.
How can you tell there's water in it?
Because it's darker.
Because you've done this experiment before?
Yes.
That's good.
Yes.
You'd like to repeat the experiment. So, look, there is water in here. There is water, and water absorbs the heat from the candle because and prevents it from breaking. Prevents the skin of the balloon from breaking. So, if I put the candle to the side here where there's no water, then it'll break.
Pop.
So this is, yeah, it'll pop. So water has a very large heat capacity. That's what we call it. A very large heat capacity. All right. So now I'm going to take this book. This is one of the books that I've written in my chemical demonstration book series. It's got my name down here. I wrote this book. It's volume 1 in a series of 5 volumes. And I'm going to open the book and read the instructions for the next experiment. So bear with me as I do that. It won't take very long. Oops. This is not an ordinary book. This is a hot book. All right, I'll be careful again here. I'll be careful. And I'm going to come out here and show you on this side, and I'll show you on the other side, that this is not a book at all. It's just the book covers. And I have 2 batteries down here. I have a wick that's soaked with lighter fluid, and there's a filament from a light bulb. All right? And what I haven't told you yet, but I'm going to tell you right now, is down here there's a small button. Can you see the button? What color is it? Okay, can you see the button?
Yeah.
All right, so batteries have stored in them chemical energy. When I open the book, I move it away from my face, and when I push the button, the chemical energy changes into electrical energy, and the filament lights up. But this filament is like all other light bulb filaments except LEDs. It gives off light energy and heat. And the heat ignites the lighter fluid that the wick is soaked in. So, here we go. Move it away from my face, push the button. There it is. Did you see it? Did you see it over there? Okay, so you tell me what happens now when I close the book. What happened when I close the book? Don't raise your hand, just tell me out loud. What happened when I closed the book?
It goes out.
No oxygen.
Fire went out when I closed the book. Why did the fire go out? Because there's no more oxygen, right? Right? So, what happens when I open the book? Is there oxygen now or not? But how come we don't have a fire?
You're not holding the button.
We need 3 things to have a fire. We need something that burns, oxygen usually from the air, and then a source of ignition. We need heat, right? So, what do?
Press the button.
Move it away from my face, right? Stop talking and do the experiment, right? Push the button, there it is. We push the button, there it is. We teach about the fire triangle so we learn how to put out fires, not to start fires. Mort, do you want to take another picture?
Sure.
Mort wants another picture, so. You happy now, Mort?
I'm happy.
Mort, tell me what happens when I close the book.
It went out.
Why did it go out?
No oxygen.
Okay, he's paying attention, not only taking pictures. He knows a lot about this. He's a retired chemistry professor. So, all right. So, let's see. Well, what happened to our two flasks over here? Which was which, right? How do we find out? We just shake it a little bit. And this one we shake it the same? No. This one we have to shake a lot harder. And the colors fade away. This can keep going on and on and on until we use up all the oxygen that's above the liquids in there. Now I ask you to focus your attention. I'll put this on this side here. Focus your attention right over here. I have a 1 liter cylinder that has a colored liquid in it. I'm going to turn the light on so you can see it better. There it is. I'm going to take a household chemical called milk of magnesia. Shake it up a little bit to make sure it's mixed well. And I'm going to add a little bit of the milk of magnesia in there. And then I'm going to take another household chemical, vinegar, that has acetic acid in it. Add the vinegar. More color changes. Do you think the color will stay the same now? Or if we wait a bit longer, we will see a different change? What do you think?
Looks like one. Green.
Yes?
Green.
We're back to the color of the indicator when we use a basic substance, magnesium hydroxide. That's what milk of magnesia is. It's an antacid. We add a little bit of the vinegar. And we see some of the colors in the rainbow. Suppose we add a lot of vinegar. More is better, right? Not always. Sometimes it's just more. So we'll watch this and see what happens as the reactions go back and forth. You're sure there's water in this one? I told you there's water in it, see? You can hear it, right? You think it'll ever break?
Only if you turn it on the side.
Well, there's a lot of water in here. David put a lot of water in here, so. Is it touching?
Yeah.
It's far enough that it even went out, right?
Whoop.
You can see the soot on it, right? All right, so remember, water has a very large heat capacity. Now, pay close attention to this because I don't want you to miss out on anything that is really exciting. You can't see it over there? I'll hold it up here. I'm going to demonstrate the most famous reaction in chemistry. A plus B. Those of you who take chemistry hear about that, right? There it is. Two clear and colorless liquids. I take what's in the beaker in my right hand and pour it in here and count. 1, 2, 3. On a count of 3, a color change happened, right? So, once again, we see that color is extremely important in many of the observations that we made. Uh-oh, what happened over here? We're back to, is this the color of the base or the color of the acid? Remember the acid was what color?
Red. Colorless.
That's pretty cool. Now it's all neutralized, it's all on the acid side. All right, I'm going to grab this, put it over here. I'm going to take a beaker that's empty except for air and a magnet that's in it, coated with Teflon. And my two friends over here, I like doing this. I really like doing this. So what I'm going to do is mix 3 clear and colorless liquids in this beaker. So here we go. I want to measure this amount carefully using the graduation marks that are on the side here. So here's the first one. All right. And I'm going to increase the spin rate here a little bit. See if I can do that. Then I go to the next one. And I add this clear and colorless liquid. Anything interesting happened so far?
No. No. No.
Well, the volume increased. Let's get this out of the way so its color does not confuse us in making the observations. And you see a slight yellow coloration now? And then I'm going to add the third one. Here's the third one. More yellow. And we get a nice deep blue color that we can observe and watch. Is there anything happening over there? What? What's happening? What does that mean? What's changing color? The beaker is changing color? The fluid inside the beaker is changing? Look, the last time I looked at the beaker, the color of the liquid in there was deep blue, right? Tell me when to look. Shall I look right now? Yes or no?
No.
I don't want to trip over anything. Shall I look right now?
No.
Yes?
No.
No, don't look right now? Okay. When shall I look? Help me out.
No.
Are you sure?
No.
What did you say? I don't want to trip over anything. Deep blue. Every time I look at it, it's deep blue.
Keep looking at it then.
Help me out on this side. Maybe you can help me out better. When shall I look? Right now?
No.
You sure? Don't want to trip over anything.
Oh my God.
Oh my gosh, it's blue. It's all blue all the time. What are you talking about? Huh? Tell me when to look.
No.
Are you sure right up right now?
Oh my God. Sure.
It's blue every time I look at
Keep
it.
looking at it.
Keep looking. Keep looking at it. I'm looking all the time.
No.
Right now. Whoa.
Oh, come on.
What is it that you are doing that I was not doing?
Looking at it.
Paying attention.
You were looking here all the time. I was looking, but not here all the time. Right? And you let me distract you by telling you, okay, tell me when to look. And you should have said, look all the time. That's just now. I let you distract me by asking you, shall I look right now? And you waited until there was a color change and then you said, now. Okay? Right? All right. This is a beautiful display of a series of colorful chemical reactions. It's one of many known such reactions called oscillating reactions. And this one is special to me for two reasons. One, it was discovered by two high school teachers, and it's named after them. It's called the Briggs-Rauscher reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. In 1973, they published a paper in the Journal of Chemical Education describing this beautiful, captivating behavior that we see here. The second reason it's special to me is that researchers, high-powered researchers, members of the National Academy of Sciences, it took them 9 years to figure out what's going on in here. That's why we do research. That's why we're patient when we do research. That's why we pay attention all the time on what's going on without any distractions. The Briggs-Rauscher reaction has in it about 8 different chemicals. It's got water, 30% hydrogen peroxide, potassium iodide, malonic acid, manganese sulfate, sulfuric acid, potato starch. The yellow color that we saw before is the color of iodine, what we in the vernacular call iodine. And it combines with the potato starch, giving us this nice deep blue color. And then we see a green color sometimes, right? You know what happens when you mix yellow and blue? What do you get? Well, there it is right there. So, I hope that you have this afternoon not only enjoyed the different experiments and the singing that we had, but you also are inspired and motivated to think about different chemical changes and to get different chemical transformations. And I invite you to visit my website where we have experiments where you can download and do at home. And the way to get to my website is scifun.org, scifun.org. Just say it a couple of times quietly and you will memorize it. Scifun.org, SCIFUN.org. But what good is it to memorize something if you don't use it? So when I go back to Madison in the next couple of days, I'm going to ask the webmaster to tell me whether we have more hits from the Boston area or not. So this will be a good telltale about your interest in doing some experiments. So I want to thank you for being here this afternoon. I want to thank the museum. I want to thank the Northeastern section of the American Chemical Society. I'm going to thank the Browner family for honoring the memory and the accomplishments of Phyllis Browner, my longtime friend. I miss her a lot. And thank you all for being here this afternoon. Thank you.